Hi there, this is the fourth video of chapter 9, which is on the constant acceleration formulae. Today we're going to look at deriving our last three kinematic equations before we then look at a few examples. So last time we looked at our first two Suvat equations, which are on the screen for you there, v equals u plus at and s equals u plus v over 2 multiplied by t. We should be comfortable with them, we should have used them, applied them quite well. We're now going to derive our last three Suvat equations. Now, each of these, similarly to the two on the screen, will have four of our variables in. Okay, so actually all of them can be derived from these two, and I'm just going to go through a process of eliminating variables. Okay, now the first one I want to work on is one that has s, u, v, and a. Okay, and so my task is to eliminate t from my two equations. I'm going to label them 1 and 2 because it makes it slightly easier for me to do my calculations. Using the first equation, I can rearrange it. I get t equals v minus u over a. I'm going to substitute that into the second equation, and I get these two fractions multiplied together. Now, multiply fractions easy. You can multiply the numerators, multiply the denominators. This is much easier for you if you notice that the two numerators are the difference of two squares. Okay, so you save yourself a step. You get s equals v squared minus u squared all over 2a. At this point, all I need to do is multiply by 2a and add u squared, and I get it in the form I'm most used to. So this is the third Suvat equation, v squared equals u squared plus 2as. If you're unsure of any of these derivations, please pause the video, try and do it yourself. If you're still stuck, then please get in contact with one of your teachers and we will be able to help you. The fourth equation is su, a, and t. So I have su, a, and t. That means I'm going to eliminate v from my two equations. Again, I'm going to label them 1 and 2. This time I don't need to rearrange any of them because my first equation there has v as the subject already. I'm going to substitute 1 into 2. I'm going to get s equals u plus at. Okay, so let's just substitute this equation into here. And I can simplify that down a bit. So s equals 2u plus at all over 2 multiplied by t. I'm going to multiply the numerator by t as I multiply that fraction. 2ut plus at squared over 2. And then I can simplify this. 2ut divided by 2 is just ut, and at squared divided by 2 is a half at squared. So I get s equals ut plus a half at squared. And that's my fourth Suvat equation, given in its most commonly given form. So s equals ut plus a half at squared. My last one, as some of you will have noticed, given that I've got the list of the four Suvat equations we've derived so far on the right, is s, v, a, and t. Okay, it's the equation that has s, v, a, and t. So I'm interested in eliminating u. So v equals u plus at, s equals u plus v over 2 times t. They're them 1 and 2. I'm going to rearrange my first equation to get them in terms of u. Okay, so I said subtracted at from both sides. Again, I'm substituting in s equals v minus at plus v. I can simplify my numerator and I can multiply my numerator. I'm just got to this point, same thing again. The 2's will cancel, and then I've got half at squared on the end, so vt net minus a half at squared. And you'll see a kind of symmetry between this equation and this equation, so between equations 4 and 5, depending on whether you've got initial velocity at the beginning or final velocity at the beginning. So s equals vt minus half at squared is this equation. So that gives us our 5 kinematic equations. These are given to you in your exam booklet, in your formula book. But you will learn them, okay? It is very, very likely you'll know these very, very quickly because we'll use them a lot. I'm going to go through 3 examples with you today. This isn't exhaustive, and actually the key thing with these, applying 5 equations, is that actually you need to be really, really focused on problem solving, okay? The same process will be used every single time where we're going to write down S, U, V, A, and T, and I'm going to collect the information from the question. Once I've done that, I can think about what I can then do next, okay? And that's going to be the same process every single time. There might be questions where you get annoyed because there isn't a clear example on this video that's going to show you how to do that. That's deliberate. These are problem-solving questions. The examiner will give you context you haven't seen. I can't show you every single possibility. So as long as we can apply these 5 equations in a consistent way, these will be relatively simple. Okay, so first example, and I've left our equations on the side here to help us out. First example is this. So just pause the video and read the question for me. Now, I'm going to write SUVAT down the side of my screen, or down the side of my piece of paper every single time. It's the first thing I do every single time because I know that I'm going to start thinking about the collecting the information. I'm also going to choose which way is positive, and I'm going to start by drawing a quick diagram. A particle starts at point A, which is 4 meters from the origin, okay, and moves in the x direction with the velocity of 32 meters per second. So I've got the initial speed of 32 meters per second at point A. It then travels to point B, which is 15 meters from the origin in the x direction, and has the velocity of 6 meters per second. And I want to calculate the acceleration of the object. Now, this isn't a perfect diagram, it's a sketch diagram, but I've got clearly shown that this distance is 4 and this distance is 15. Because the key thing here is I want to calculate the acceleration, so my question mark goes by A, but I don't have enough information yet. So I need to work out, and I need to think about, have I got any information about the time? The answer to that is no. Have I got information about displacement or distance? And the answer to that is yes, but I need to be clever. The information I'm given, I've got initial velocity at A and a final velocity at B, so I'm interested in the displacement from A to B. The distance from O to B is 15 and O to A is 4, so the displacement or the distance from A to B is 11 meters. Okay, is 11 meters. They will occasionally give you distances and get you to calculate your own displacements. Importantly, if you've got initial and final velocity, the displacement is the distance between the 2 points of which you have those initial and final velocities. So this will be 11 meters, and it's in a positive direction as well. Calculate the acceleration of the object. Now, same as before, I need to identify which equation I'm going to use. I've got S, U, V, and A, so I need to look at my equation. So I'm going to look at one that has S, U, V, and A. So neither of the first two. Now, these two also have T in them, so this one, S, U, V, and A. I'm going to use the third equation. V squared equals U squared plus 2AS, sorry. Now I'm going to substitute, and then I can start solving. That should be nice and simple, and I should get the answer negative 44.9 meters per second squared. Once you've got that answer, I want to just kind of sense check it a little bit. I want to have an idea of whether that makes sense. This is a deceleration, so as obviously my thing should be getting slower, and actually this makes sense in this context. Okay, I've got an acceleration that goes in the opposite direction to the velocity, and therefore I should have the velocity going down, which I do. So this answer does make sense in the context of the question. That's always a useful way of checking whether you are correct or not. Now, the second example, slightly more complicated. Again, pause please, and read the question. Now, this question, I've got a spring oscillating back and forth, and as the mass falls, it passes the equilibrium point of velocity of 9 meters per second. Now, again, I'm going to put S, U, V, A, and T down the side, and I'm going to draw myself a diagram. I've got positive as downwards because it's talking about a mass falling, and I've got an initial velocity of 9 meters per second. The spring causes the mass to accelerate towards the equilibrium point at negative 50 meters per second squared. Find the times that the mass is at the point with displacement 0.5. So I want to find the times and the displacement of 0.5 meters. Okay, 0.5 meters. Importantly here, I've got some initial velocity of 9 meters per second. It's still going in the positive direction, even though my acceleration may be going back towards the equilibrium point. Now that makes sense with the spring, because we know that the spring is going to slow that thing down until it stops and then return it to the origin, to where it started. Once I've got this, I've got 4 variables or 4 things marked on my list here. I want something that has S, U, A, and T. So I'm going to look at my equations, and I want the 4th equation, which has S, U, A, and T. Once I've got that, I'm going to write my equation down. I'm going to start substituting. Okay. Now you'll notice at this point I've got a quadratic equation, which I can rearrange to this point. 25t squared minus 9t plus 0.5 equals 0. Now, because it's a quadratic equation, when I type this into a calculator or use the quadratic formula, I'm going to get 2 answers for the time. Now, both of these answers are positive, so they're both valid. Times can be positive, that's absolutely fine. But I need to understand what this is asking me, or what information is telling me, because occasionally I need to interpret this. I've got a situation where a mass on a spring has travelled 0.5 meters having started at a speed of 9 meters per second. It's passed here after 0.7 seconds. It's then continued on, and at 0.29 seconds is back at this point. Because this is what this equation has told me. The information I've put in is that it's at displacement 0.5. It doesn't know which way it's travelling. My equation has no idea which way it's travelling. It's just saying that at this time it's at this point. Now, that means that after 0.29 seconds it's back at this point, and that makes sense given the fact that I have a negative acceleration. So my mass is falling, passing through 0.5 meters, continuing on to some point which we haven't calculated, and then returning back. So 0.29 seconds after it leaves this point here, it then is back at this point on its way back towards the middle. And that makes sense in the context of the question because we've got a spring. Okay, so both of these times are valid. Occasionally you might get asked to find the difference between the two times that it passes this point, and then we'll just subtract one from the other nice and easily. Okay, now we're going to look at an example in a second which might not be quite as easy to interpret, but this one of two positive examples. I've got a negative acceleration, so an acceleration going against the velocity, the initial velocity, and so it will slow down to a stop and then return. Okay, we'll look more at this kind of motion when we start looking at motion under gravity, which will be in the next video. I've got one more example for you before you get started on the pre-quiz and then the sheet, so let's have a look. Your third example is on the screen now. Have a look at it for me and have a read through, and then we'll get started with our explanation. Now, same as always, I'm going to list my variables to begin with, and I want some representation of the way in which what this problem looks like to help me visualize it. So I'm going to define a positive direction, and I'm going to draw my diagram. I'm told in the question that the arrow is subject to a deceleration of negative 4 meters per second squared, so I'm going to write that next to A straight away. It says at a displacement of 80 meters, so S equals 80 meters, the arrow has a velocity of 46 meters per second. I want to know how much time has passed before the arrow is 80 meters away, so I'm interested in the time. Now I've got 4 variables listed there with something next to it, so I've got S, V, A and T, so that means I'm going to use my 5th Suvat equation. I'm going to plug in my answers, my information. I then get a quadratic, and I've got 2 answers there. Now, time will always be positive, okay? So if we've got 2 answers, one of which is negative, then straight away I can write that t equals 1.62 seconds, okay? Now, we have a negative answer there, and in a second, I'm going to go through part B first, but after that, I'm then going to try and explain what that negative answer means for anyone who's interested. But let's look at part B to begin with. It says that to calculate the velocity of the arrow when it's released. Key thing here, okay, we can, for part B, given that I've calculated the time at the point when it's 80 meters away, and especially because my acceleration hasn't changed, I can use the same Suvat list of variables. I don't need to rewrite them, but I can replace t and say that t equals 1.62 here. And I might be tempted to try and use this calculated variable when I'm trying to find u, which is the thing I'm now trying to find. Okay. What I'm going to suggest to you, and the reason I'm going to go through this, is actually, despite this being possible, I'm going to suggest to you to always try and use the 3 variables you're given in the original question, okay? That means you're going to avoid any situation where you carry an error forward. So I'm going to ignore t equals 1.62, in part because that number that's rounded anyway, so I actually want to make sure I'm using a full number, but also because I don't know, or you won't know in an exam or in your working, whether you're definitely correct in part A. So if you can avoid using something you've calculated, please do. So that means I'm using S, U, V and A. So I'm using my third Suvat equation, V squared equals U squared plus 2AS. That means that I can just plug in my numbers and solve it, and I get U is plus or minus 52.5 meters per second. Now, again, I have a couple of different answers, and I can say that I'm interested in the positive answer. I know that I've shot an arrow this way. That makes sense given my initial or my time. Okay, so I've shot an arrow in the positive direction and it's lost some speed. And after 1.60 seconds, it's at 46 meters per second. Okay, so that's those questions answered. that makes sense. Those answers make sense in the context. I'm now going to try and explain a little bit about why both of our answers are chucking out a negative answer. Now, I think this is really important and can be relevant for us as we start thinking about the models more deeply. This isn't something that you will be examined on, is the first thing to say. So if at this point you feel comfortable and want to just get started on the pre-quiz and the sheet, by all means do. If you're interested in kind of a deeper understanding, then please do carry on listening. We'll start with the first answer, where we've got two answers, one of which is negative. The important thing here is to understand the way in which this model works, okay, and actually what information we're giving it. This model is being told that we want to find the time at which the thing, so the particle, really, that we're modelling it as, or the arrow, the time at which the arrow is 80 metres away from this origin, has a velocity of 46 metres per second, positive 46 metres per second, and an acceleration, which is constant, of negative 4 metres per second squared. So I want to find any times, okay, that the arrow gets to this point and has these under these conditions. Okay. Now, I do not have a sense, or my model does not understand that time only goes forwards. Okay, because it's just maths. The model has a sense that I could put everything in reverse. Okay, so time can get bigger in reverse, and we can move backwards in time. So what this is saying is 24.62 seconds ago, if I go in reverse from this point, I can have a situation where an arrow reaches this point with this speed 24.62 seconds ago. So the way that motion would have worked is saying that 46 meters per second, this v, okay, is the speed at this displacement. And so what has happened is that this is telling me that the arrow has gone past this point, this displacement, and then come back again to pass this again because I've got negative acceleration. So my arrow's gone all the way past here and then come back again, assuming that this negative acceleration can generate that. Okay. Now, we get confused and will struggle to understand why this is in the past. Okay, but the model has no notion of the past or the future. It just knows that I can forecast the model will work in either forwards or backwards. Okay. So because we know that time is going to only go forwards, we're comfortable just saying we can ignore this negative. Key thing is, though, this negative answer in some cases, and this is especially true when we look at motion under gravity, can actually give us like a bit of a sense check. It can help us to understand exactly what the model is telling us. So in this case, this negative 24.62 seconds is quite difficult to really understand. Okay. But it is an answer to the question, given that the model does not understand that time only goes forward. So the key thing we have to know is that because time goes forward, I can just ignore that and go for positive straight away. For part B, I've got plus or minus, because if I square root something, both are valid answers. So what this is telling me, because I've inputted a final speed, an initial speed, and a distance, okay, this is telling us that I could either have a positive or negative initial velocity. Okay. Now, either having a positive or negative initial velocity means that my positive velocity makes sense to me because I have a negative acceleration going this way. Okay? A negative acceleration going this way. Now, I will have released, and the context of the question will tell me that I've released my arrow going in the positive direction. I've got a deceleration, and it slows down to this point. Okay. Now, this links to this negative time here. If I reverse my model, then u and v will switch over. And actually what this is telling me is that with negative acceleration, I can reverse time and get back to this point with a negative velocity. Okay. So again, we want to think about the context and give the answer that makes sense in the context. but we're not just going to dismiss any other answers as stupid or completely incorrect, because there are contexts, and this is true when you start getting into if any of you go on to do physics at university, there can be contexts when you start forecasting in negative time, and it gets really, really interesting and really quite difficult. Okay, so right now the reality is, for you at your level, that we're not interested in negative time. We are going to focus on positive time. We're going to look at velocities and things in the context of the question and give the correct answer. But anyone who's interested, there are ways in which we can understand, and I'm happy to talk to you about this in more detail, ways we can understand this time changes and the way in which time moves negatively, and we can get different answers from these models. That does show us something else about the models and gives us a deeper understanding. So I suppose the point of that is to deepen your understanding and spark your interest a bit. If you would like to talk more about this notion of negative time, then please do talk to me. I'm happy to have that conversation. But for the key thing for the answers to these questions, we are focused on what makes sense in the context. Okay? So as all good mathematicians will, we will interpret the answers we're given in the context of the question. So if you haven't already, please do have a go at the pre-quiz and then have a look at the sheet. Any questions, please let us know.